Hi and welcome. Today we'll be talking about the elevator problem, specifically what happens to you when you stand on an elevator with a weighing scale moving upwards. Well, what would your mass reading be? It would kind of look like it's going up, then it's gonna go constant, it's going down, and it goes back to constant. Why is this the case? Let's first look at all the forces acting on you and then on the weighing scale. On you, there is a force of weight by Earth on you. There is also normal contact force by the weighing scale on you. I'm just ignoring the magnitude of the normal contact force for now. And because of this, using Newton's third law of motion, that if body A exerts a force on body B, then body B must exert an equal and opposite force on body A, aka action-reaction, there must also be normal contact force by you on the weighing scale equal in magnitude. This is what causes the mass reading, not by weight directly. The weight would affect the amount of normal contact force you exert on the weight scale, which then directly affects the mass reading. So, let's go ahead and see what happens. At first, the lift would be accelerating upwards because it goes from being at rest to moving. So there must have been some form of acceleration to get it going. Since the lift is accelerating upwards, by Newton's second law, there must be a net force upwards. And since you are on the elevator, you are also experiencing a net force upwards. This means that overall, all the forces acting on you should give you a net upward force. Well, what forces are acting on you? There's weight and normal contact force, which means that the normal contact force by the by the weighing scale, on you must be more than your weight by Earth on you. This is so that there is an overall upward force. Since there is a greater normal contact force by the weighing scale on you, using Newton's third law of motion, there must also be a larger normal contact force by you on the weighing scale. And this means that you would have a greater mass reading, as you can see right here. It is higher than usual. Now, T1 to T2 is when the lift is at constant velocity moving upwards and it's in the middle of transporting you upwards. So when this happens, there is no net force using Newton's second law or first law, up to you. Since there is no net force, there should be no net force on you either, which means that your weight should cancel out with normal contact force. Which means that this is as good as you standing on the weighing scale at when on the ground that isn't moving. So the amount of normal contact force you exert on the weighing scale should be the same. And this is why it would be the same as if you were on the ground, as you can see on the graph. Finally, let's go to the last instant, when the lift is going to be accelerating downwards or decelerating so as to come to a stop because we have reached our destination. Since there is a net acceleration downwards, there is going to be a net force downwards, as stated before. Since there is a net force downwards, overall speaking, you will also have a net force downwards, and so overall speaking, there must be all the downward forces acting on you should be greater than the upward forces acting on you. So your weight is unchanging. Your weight won't change unless you leave Earth, but your normal contact force would decrease. This is so that you can have an overall downward force. Since there is a lower amount of normal contact force by the weighing scale on you, there must also be a lower amount of normal contact force by you on the weighing scale, which is why, overall speaking, you have a lower mass reading when the lift is coming to a stop. And this explains why you feel like you're kind of almost floating, I guess, because you have a lower mass reading on the weighing scale. Thank you so much for watching, and I'll see you guys next time.